Okay, welcome back to session 19 on plane stress. This is our third and final portion, treating Mohr circle. And in this portion, in this part, what we're going to do is look at more examples of how we might use Mohr circle, but now we're going to look at structures. Okay, so in the previous portion, we were looking just at the material elements. And now we're going to say, okay, a material element's on a structure, it's under load. What does it look like? And what does it look like when we perform a transformation? This slide we've seen before, and it's discussing kind of what we can do in Mohr circle. We can find stresses in an arbitrary orientation. It's a little bit tedious, not what I consider to be the most novel portion of using Mohr circle, but finding principal stresses and finding maximum in-plane shear stress, these two aspects of Mohr circle are really fast, or can be pretty fast, and are powerful. So let's go ahead and look at our first example of a situation where we will have a structure that's under load, and we can describe the stress on an element in this structure through Mohr circle. Sorry, it's a little bit messy. It's a little bit late tonight as well, so I'm a little bit tired. Anyway, so we have here our bar, and it has cross-sectional area A, and it has some force P pulling it apart. And we can know that the stress here is sigma 1, or sigma is equal to P over A. Now, why did I say sigma 1? This is actually, the standard way we think about this is actually kind of already in a state where there's no shear stress, okay? And we can describe this P over A as a principal stress. So it's one of the larger ones. What are the other principal stresses? Well, we're maybe jumping a little bit, okay? We're doing in plane, all right, stresses at this point, or plane stresses at this point. But yes, there's one in an orthogonal direction to whatever plane we pick that's also going to have zero stress, okay, with an element oriented appropriately. So if this is x in that direction, we can say that sigma 1 is in the x direction, okay, and y could be either left, right, it could be coming out of the board. It doesn't really matter for this particular problem. But we want to pick an element that has plane stress on it. So because that allows us to do our transformations in Mohr circle and kind of be able to do rotations, right? So here we have Mohr circle. It's already kind of drawn, and you're like, oh, there's some distracting stuff over here. My bad. Okay, forget the distracting stuff for a second. This is tau in the positive downward direction, sigma in the positive right direction. What's the middle going to be at? Well, the middle is going to be the average. Okay, it's just the average of P over A and 0. So it's going to be P over 2A. That's where it's going to be. The principal stresses we've already described have sigma 1 out here at P over A, sigma 2, sigma 3 equal to 0. And I just said this a second ago. It's just sigma 1 over 2. Okay, or I said P over 2A, which is sigma 1 over 2. And then if we want to go from this state where there's no shear stress, we can rotate 90 degrees on Mohr circle or 45 degrees on the element to get to a state where we have maximum shear stress. Now, often we draw maximum shear stress downward, okay? It's kind of, we should be somewhat careful about how we do this, okay? But if we go 45 degrees, we can say that the tau max is going to be minus sigma 1 over 2, okay? So here we have our 45-degree angle shift, okay, we are going to say, so if this were x, okay, or we can describe this is wrong. Okay, this is wrong. I didn't fix this. Okay, because oh no, this is right. Sorry, that's so late. I'm sorry, guys. This is right. Look, we're rotating by 45 degrees. Okay, our tau max has gone negative. All right, because it's up here, so it's a minus tau max, and the average stress, it's the same. Okay, and it's just sigma 1 over 2. So both of them are coming out here. All right, and if we've gone the positive 45 degrees or the positive 90 degrees, okay, this x out here, right, is now really up here. Okay, so this is like the sigma x prime, right, which is what you see there, x prime direction, and the y prime direction is over here. So you see how tau, now in this corner where you have x prime, y prime, right, if I drew this one first, it's going the opposite direction, right, of what we usually use for the positive convention. Okay, so what's the point of this example? The point is a couple fold. One is, you often think there's no shear stress involved with axial loading. But we've said, and we'll talk about this again and again, that ductile materials fail primarily due to shear. Okay, and we'll talk a little bit more about maybe why that is later. But if that's the case and there's no shear here when we're looking at the principal stresses, which is kind of the uniaxial case, what we normally do, it's like, wait, how could it fail? Well, it's because if we rotate the element 45 degrees, there is shear. This material is experiencing a shear stress. Okay? And failure might occur at a slight angle, at 45 degrees, for example, or there might be lines that form for a ductile material, okay, because that's the direction the shear stress is highest. And also we see that in this state of stress, when we've gone 45 degrees, we still have, this is not a pure shear case, obviously, but we still have normal stresses involved. And the shear stress is negative, okay, according to our convention. If we had gone the other direction, okay, then look, sigma x prime would be coming out over here, sigma y prime would be coming out over here, and then this would be the tau x prime y prime, and that would be a positive corner. Okay, so the circle, or the direction we go in the circle, helps us determine whether or not the resulting stresses that we have are going to be positive or negative. And right here, mostly, I mean, what we're seeing is we haven't really dealt with negative normal stresses, but they do exist. Okay, you can have that, and you can draw that out here. So that's uniaxial loading. Pure shear. So here's an element on a shaft that's being twisted. T-ap, T-ap, and like you see here, and we have X, all right, coming out this direction. This is the X direction over here. So if we draw the X direction this way, maybe we want to draw our tau xy, okay, in that direction. Now remember what we've talked about before. I think the easiest way to visualize which direction these arrows go when it's on the surface of a shaft under torsion is to think about how the shape is twisting, right? So we've done this before. Like if I drew these lines coming across, right, as it's twisting, it's not very good. Let's see if I can. If I start here and I go there, start there, go there, right? Things are getting distorted like this. That wasn't so good. they're getting distorted so that the elements are being shifted with these stresses. Okay, as we're seeing, this side's going this way, that side's going that way. Okay, really badly drawn. Okay, but you can kind of visualize that's how the elements are being twisted. So they go on the, so typically like this side's going to go with this direction, this side's going to go with this direction. Once I know one, I can draw the rest of the shear stresses on this element because I keep it in equilibrium. And if I want to kind of make it more standard looking, I flip it through this line. So now X is going this direction, and now this is kind of the more positive, or this is more of the natural convention that we use. And we can equate this shear stress to the TC over J, or T rho over J if it's not at the outer surface. How do we go about figuring the Mohr circle or drawing the Mohr circle? Well, the average stress is the average of sigma x and sigma y. There's 0 here, so they're going to be 0. So where's the center? Well, now the center is at the middle, is at the origin. And we can draw the state of stress like this, where we have our maximum down here and our minimum here, or the negative of the maximum up here. And look, we're already in a state of pure shear. There's no normal stresses on this element. So we have a situation where we have maxed out the shear. So in the uniaxial case where we were stretching it just a slide ago, what we had is a situation where we were set up for principal stresses. But then in this case, with pure shear, we're set up from maximum in plane shear stress. Okay, so like the opposite. Now, if we want to get to a state of principal stresses, what do? We will need to rotate to get to these locations over here. So we rotate by how many degrees? Well, on Mohr circle, we're going to rotate 90 degrees. On the material element, we're going to rotate 45 degrees. So what does it look like? It looks like this. We have our element. It's been rotated. That's kind of my rough approximation for 45 degrees. And now we've gone from a situation where we had only shear stress to not having any, okay, because we're in the state of principal. When we're in principal, when we have principal stresses, when we're looking at our principal stresses, there's no shear, okay? When we look at maximum shear, there's often still normal stress, but that's a cool thing about principal stresses is that you get to a state, you can always get to a state where there's no shear. And sigma 1 is positive coming out this way. Sigma 2 is negative going in this way. All right? So this is compression and this is tension. It's kind of interesting. It's an interesting pattern, okay, to see here. And this element is what we would be experiencing if we look at the normal stresses. Okay, let's do another example. Last example, and then there will be a question. Cylindrical pressure vessel. So we've seen this before. We have some internal pressure. We have an element. The hoop stress in this case is in the y direction. The longitudinal stress is in the x direction. Has radius c, bulk thickness t. You're like, okay, I already know what the normal stresses are going to be, but just give us a second. All right, so here's x and y coordinates. And we're saying this is sigma x, this little arrow there. Okay, in this axis, and then we're going to say this is sigma y. That's the hoop stress direction. Sigma x is PR over 2t. And this is the longitudinal stress. And sigma y is PR over t, twice it. So what's the average? Well, the average is going to be the average of these two. So halfway in between is 3 PR over 4, is 3/4 PRT essentially. What is the shear stress in this case? Well, there's none. Okay, there's none in this particular orientation. Okay? So that's just going to be 0. So once again, we found ourselves just by looking at this element. Right? We don't need to do anything. We just know that we found ourselves in a state with principal stresses. So where are the points going to be? Well, they're going to be, one's going to be out here at PR over T. It's actually the sigma y will be sigma 1. And the other one will be at PR over 2T. What's the radius? Well, the radius is going to be, say, PR over T minus 3 PR over 4T. Okay. So that would be PR over 4T, not PR over AT. So that's, and we see these principal stresses as such. Okay, sigma 1 is PR over T, as we said previously, and sigma 2 is PR over 2T. We see there. If we want to figure out maximum shear stress, what do we need to do? Well, we need to go from this state, okay, and rotate to get to the top and the bottom. And how much are we going to rotate? Well, we got to rotate 90 degrees. Okay, now we have the option to rotate either that direction or this direction. If we want sigma x, okay, to kind of become positive, or to have a positive shear stress on that side, okay, we're going to actually, we might want to rotate minus 90 degrees, okay, on Mohr circle. So we'll do it that way. And that corresponds to an element rotating 45 degrees, and x prime, right, was this direction, and now is rotated 45 degrees downward. Y prime is now this direction. And when we get to this state of max shear stress, we have the average normal stresses, okay, being the same, okay? So this is not correct. This should be like that. Okay, sorry, that doesn't look good. Just ignore that down there. That's a lot of hair. Okay, it's late. So the average stress is the same, right? Because it's vertical like we have here. And the maximum shear stress we're defining as down here, so it's positive. So it's tau max like that. Okay, and so that's what you see right there. The tau max, all right, is equal to R, and that's equal to PR over 4T, like that. Okay, I'll just rewrite it so it's more clear. Like that. Okay. So this concludes our examples. This last one, number 6. And we're going to have one problem, okay, to do here, which is looking at a thin-walled spherical pressure vessel, okay, with a radius r and wall thickness t. It has internal pressure, okay, P. And the question is, where's the center of Mohr circle? And then what is the maximum in-plane shear stress for this configuration? To conclude this session, we have derived Mohr circle. We have described how to construct Mohr circle. And we've gone through examples on material elements. And we've also looked at examples on some of the structures that we've been analyzing in this class. I hope you find this information useful. And as there are systems with combined loading, okay, then there's an opportunity to figure out what the state of stress is, okay, at least planar stress, for the types of configurations that we're primarily concerned with, and then figure out how you can figure out principal stresses and max shear stress. Thank you, and see you soon.